G'day everyone, welcome to Lubrication Experts. And today I think I've got a topic that's actually been requested a couple of times on the YouTube channel. And it's to talk about polymers in kind of all of their variants as it relates to both lubricants and greases. So I had to find someone who is really up to the task because it is such a specific subject. So today I have Dr. Jacob Scherger with me from Functional Products. He's the senior polymer scientist. So if you thought that there are some job descriptions in our industry which are pretty specific, this to me gets about as specific to the topic at hand as we could find. So I'm very lucky to have Dr. Jacob here. And so Jacob Scherger, thanks for joining us.
Yeah, thank you. Good to be here.
Awesome. So I think what would be helpful is if we start with some like very basic definitions, not just for the audience, but for me. I don't really have a chemistry background, so I'm always kind of fumbling in the dark around here. Um, First of all, can we give just like a generic definition of what we're saying is a polymer? And then maybe we can then drill down a little bit more specifically to the types of polymers that we talk about when it comes to lubricant formulations.
Yeah, I think kind of the most basic definition you get with a polymer is any molecule that's made up of just repeating units. So polyethylene is a whole bunch of ethylene hooked together. Polypropylene is a whole bunch of propylene hooked together. And then once you get big enough, it becomes a polymer. Uh, I People will argue about at what point it becomes a polymer. That's depending on who you ask and what the application is. People tell you all sorts of different things. I think the most useful way is when you have enough units hooked together that it gains unique properties different from what it was when it was a small molecule, you've got a polymer. So if you've got, say, polymethacrylates made out of alcohols, I think everybody's familiar with the consistency of alcohol. It's a liquid. It's got a certain smell, all of that. You hook enough of it together and it becomes a bouncy, squishy rubber. They're clearly different. You know when that's become polymer. So the properties have changed. And then kind of the gray area in between, we throw a term at, we just call it an oligomer. It's almost a polymer.
What's kind of resulting in that change? Is it simply that we have modified like the physical shape of the molecule sufficiently that it gains extra properties, or are we changing the chemistry in any way by extending it?
There are some polymers where you're changing the chemistry, but mostly it's just the physical thing. It's those molecules are constrained. They can't move around as freely and they have to move with another molecule then. So degrees of freedom goes down. The way molecules can move through each other goes down. They kind of end up linking together when they're big enough, like you got a bowl of noodles and you got just one noodle there. It's, it flops around or whatever, but you have a whole bunch and it touches all the other ones and it does something. And that gives it kind of that physical form attached to it.
Mm. Okay, and so what are the maybe like common polymer types that we're talking about when it comes to lubricant formulations?
There's quite a few actually that end up getting used in lubricants, what we call OCPs or olefin copolymers. So I'll just tell you what a copolymer is. If instead of hooking a whole bunch of one thing together, you hook a whole bunch of two things together, you've got a copolymer. But the most common OCP is ethylene and propylene. They'll show up in a lot of lubrication formulations. Polybutenes, polyisobutylenes show up. Polymethacrylates, I typically see that shorthanded as PMA. Styrene copolymers. Depending on who you ask, some people might call an MPAO polymer, or they might just call it a heavy base stock, but really you're hooking those molecules together, you're making what is technically a polymer. And then each of those things, what they do, how they work, their properties are going to be pretty dependent on molecular weight. That's just how big the polymer is. The more you have hooked together, the bigger the molecular weight. And the architecture. So things can all be together in a straight line like a noodle. Things can have chains hanging off the side, more like a comb or a star. And all those different architectures change the properties, change how they behave in oil.
Okay. So maybe if we can start then moving into the use of polymers in lubricant formulations, um, it'd be good to get an idea of um, what kind of properties they're imparting to the final formulation. So some of the common ones that you've mentioned then, for example, like the polymethacrylates are obviously a family of different polymers that have different use cases within the lubricants industry. So could you please just describe how, like you said, changing the architecture of something like a polymethacrylate can lead to different use cases?
Yeah, absolutely. So polymethacrylate can be used like any linear polymer, just as a viscosity modifier or a viscosity index improver. And those, the more linear and the longer they are, the better they tend to be as a viscosity index improver. And that's because as you put something into a colder oil, there's less solubility and the polymer kind of compacts down and isn't taking up much space. So it's adding a small amount of viscosity. As you increase the temperature, that drops the viscosity of the oil, but increases the solubility. So that long polymer fans out and takes up more space, increasing the viscosity more, which allows for less viscosity drop, higher VI. Now you change that and make it more branched. So the same weight of polymer can't ever expand to take up more space. It's hooked to itself with that branching. But those side chains might serve a different purpose. Those side chains might allow you to have fewer points where they're susceptible to shear. So you might have a lower shear polymer by increasing the branching. You might make those side chains appear waxy. Make them appear waxy, they actually gather wax out of an oil, and that's how they can be used for pour point depressants. They'll gather that wax and prevent it from making crystals and freezing, improves low temperature fluidity. If you just keep expanding the molecular weight, make it bigger and bigger and bigger, eventually you'll get into a regime when it's not in fluid, it's called entanglement regime. But in the fluid, it will be semi-dilute or might still be called entangled once you pass semi-dilute. But usually we stop at semi-dilute. But the chains can directly interact in the fluid again. And then you get things like tackifiers, things like anti-mist, because they're holding the oil in with them. And then some of those side chains or side hoops you might attach other molecules to kind of change the solubility or change the polarity. And if you get that just right, you might get something that is kind of borderline soluble, which works as an anti-foam agent then.
Yeah. Okay. Cool. Well, I mean, that's super helpful because we always hear about. I mean, on the end user side, we always hear about these polymethacrylates, right? And then they say that they're used for pour point depression and they're used for viscosity index improvement, and we use them to, deal with foam and all that kind of stuff. And you think, how's it possible that one molecule is doing all this stuff? And not only that, but on the end user side, we don't really see them, right? We don't detect them because there's not a used oil analysis test that picks up that kind of additive. Really, you only kind of see their effects as they start to shear down, for example, where you might see the viscosity at 100 drop slowly over time in a hydraulic oil or something like that. So there's not like a direct measurement for that kind of additive. So it is interesting to see, like you were saying, how changing the architecture can also change its function so much. One of the other ones, or the group of molecules that you talked about as well, which I think it might be helpful to understand because they're in so many formulations, is the polybutenes and the polyisobutylenes as well. Because I think, again, from the end user, the names are pretty similar, so everyone thinks of them as being the same thing. Could you please describe, the use cases for both of those molecules and how kind of the architecture of those molecules leads to their function?
Yeah. So polybutenes are actually a copolymer of different isomers of butene. So they end up with kind of chains sticking out kind of randomly off all the sides. And so they work nicely as a low shear thickener. They tend to be restricted to those low shear thickeners just because of all the random isomers. It's hard to increase the molecular weight to a point where they'd be high shear and providing very high efficiency viscosity increase. When I talk about efficiency, I'm talking about like increase in viscosity per weight percent treat. So they're limited in that, but also being low in that keeps them very low shear, almost like base oils. So you don't need to worry about them shearing out nearly as much. Polyisobutylenes, PIBs, are a single isomer. They're very ordered, and that allows them to get much higher molecular weights. So you can use them like a PB. You can get the low molecular weights that will perform almost the same purpose. One of the differences you'll see there is because they're so ordered, they may order themselves at low temperatures more. So you may run into more low temperature problems if you overtreat with that, though they don't just inherently cause that. But you can make them very big and they can become things like tachyfiers. They can become all sorts of things that you can do with a high molecular weight when you don't need low shear as well for those PIBs.
Yeah. And so I might be speaking out of turn here, but I mean, I've seen polybutenes mostly used to, like, let's say, for example, boost the viscosity of something like something with a vegetable base oil, right? Where a lot of the vegetable oils are only available in low viscosity grades, and people are trying to make something that's, a biodegradable but higher viscosity, and so then they just boost the thing with polybutenes versus a polyisobutylene, where is it correct to say that they're part of a lot of dispersant packages?
A lot of dispersant packages use polyisobutylene as kind of a base or something to help keep it soluble in the nonpolar oil, because the dispersant part has to be very polar. But that's a modified polyisobutylene. That's something that's going to have probably nitrogen groups attached, or something that's polar, that's going to help to pull those contaminants out or keep them bound up. So if you just get a polyisobutylene by itself, it's not going to do that. But if you have a modified one, something with nitrogen or some other dispersant chemistry attached to it, they are a good delivery system for those. You can do the same thing with PMAs, C dispersant PMAs as well.
Cool. Now, one of the variations is always kind of trying to match your additive chemistry to whatever base oil you're using. So let's say, for example, in the more extreme scenario, when you're picking between, let's say, for example, a base stock that's a PAO versus something that looks like a oil-soluble PAG, how would that change the type of polymer chemistry that you can select?
So you want to match your base oil type to the polymer type. You want to make sure you have something that is soluble. Solubility is the main concern there. And where polymers are concerned, when I'm formulating with them, how I like to think about it is that the oil you've chosen has a certain amount of solubility available, and different polymers are going to take up different amounts of that solubility. And you need to still have room for your additive packages afterwards and everything like that. Everything has to take up that certain amount of solubility. So some polymers might be perfectly soluble and work very well in the oil by itself. When you go to add an additive package, you find that everything gets cloudy, everything goes hazy. That's you've used up too much solubility, and you can get some of that back by doping small amounts of something that adds more solubility, like an ester or an alkylated naphthalene. you can get some of that back by, instead of using a whole bunch of one type of polymer, use two compatible polymers. So in typically in mineral oil with all of these non-polar polymers, I don't see a lot of solubility issue. You might need something to compatibilize the package still, but usually a very small amount. For a PAO, they have less solubility to them in my experience for polymers and additive packages. So what we've had a lot of luck with is we have some PMAs that are designed to go well into PAO, and then they are slightly polar themselves, and they add a little bit of solubility back. So you can use some PMA, some PB or PIB together and have a more soluble, better result than if you had used one individually. And it's hard to give you a general rule. It's kind of a case by case basis. You look at what additives are being used. Everything has to work together. So it's hard to make any general rule for any of that. But choosing base oil is definitely important. In addition to just being able to be soluble, the solubility changes other properties. So if your polymer is more soluble in oil, that's going to change how it affects how much viscosity is being added, how much VI is being added. If your polymer is very poorly soluble at room temperature, but very well soluble at high temperature, that's going to give you a bigger boost in VI. But if you're strongly soluble across the board, you're getting more viscosity per treat. You just need to get that viscosity up.
Yeah. Okay.
Different things like
that. That makes a lot of sense. The other question I had was, in a world where, let's say, for example, regulatory pressures are increasingly important, let's say, and there's increased interest, I think, in biodegradable type lubricants, first of all, for environmentally sensitive applications, but I think people are wanting to turn to them a lot more just as kind of like a Band-Aid solution, right? To be able to say that they've done everything possible. And then maybe the other side of that coin is also food safe formulations as well. So and there's obviously a range of polymers that can be biodegradable, or they can be food safe. What are the types of properties from the polymer world that make them biodegradable?
It's really the chemical linkages in there. Your PMAs with the oxygen linkages and double bonds and things like that tend to be more biodegradable because they can react and split apart and change. Though the double bonds, you want to be careful because you don't want those reactions to do what's called cross-linking. You don't want the polymer chains to react with each other and make your oil into a gel. You don't want to suddenly have your liquid lubricant turn into Jello. That would be not great. That's a technical term, not great. Yeah, those will help the polymers biodegrade, though more frequently what we end up seeing and doing is using polymers that are not themselves biodegradable, but are able to go in low amounts and facilitate other biodegradable things being able to be used. So rather than needing to use heavy bright stock or something that's not at all biodegradable, you could use polymer that's soluble in, say, canola oil, and it might only end up needing to be 3% polymer to get to the viscosity you need. And then the rest of that percentage is bio-based canola oil that you've been able to add that is now biodegradable, that is now safe, that it wouldn't have been in the formulation before. And polymer facilitates the addition of, even a non-biodegradable polymer facilitates the addition of biodegradable components by upgrading those, or allowing things to work together more efficiently. And then food grade, I think you mentioned, a lot of the requirements for that are, they're largely determined by kind of the reaction conditions and how pure you can get the polymer. You get your polymer to a sufficient molecular weight, and it's a polymer of a type that is going to break down into non-hazardous components, can be food grade. But what you don't want is something that's been kind of poorly refined, so to say, that has a lot of very small molecules still in there. You don't want catalyst left over in it. You don't want like oligomeric pieces that might actually be able to get into something and bioaccumulate. You want it big enough that they can't penetrate a cell and bioaccumulate.
Yeah, right.
And that's really kind of trick to bioaccumulation in food grade.
Yep.
Is just having sufficient molecular weights and everything reacted properly. So there's not a bunch of small junk with the big stuff, which it's called having a narrow PDI, polydispersity index, if you want the technical term.
Excellent. We do love technical here. So, okay, I think that's super helpful for understanding, the different types of polymers that we have in lubricant formulations. Maybe a generic question to follow up. What are some of the, let's say, common misconceptions or myths that you see about the use of polymers?
Well, I end up seeing a lot of different misconceptions that comes from different places. And I think what happens is you get a formulator, they've been there a long time, they tried a polymer in their system, didn't necessarily know what they were looking for, just picked any old polymer, wasn't compatible with what we were doing, and they decided, well, this is what polymer is going to do. We're not going to do that anymore. And really, it's down to choosing the right thing rather than that's what all polymers are going to do. Especially with older chemistries, or people are using like natural latex, so it's tended to kind of burn when heating to mix and caused a lot of like clogged filters and things like that. But you're not going to see a polymer necessarily just be clogging filters. That's happens when solubility is poor and they start to come out of solution. That's when something's going to get in your filter, just like any other additive component. Something else I see a lot is that you can't add a polymer to a high shear application because it's going to shear out. It's going to cause all sorts of problems. That can be true, but that's an issue with using too high molecular weight of a polymer. To use something lower, polymers will get down to, I've seen polymers with pretty good properties that shear as low as 4% in KRL. It's really more of a base oil level of shear for some things than a polymer, but you can find those just to choose your polymer properly.
Yeah, right. Okay, cool. The other obvious application of polymers in our industry is greases, right? And I'm guessing there's going to be some overlap, but in what way are polymers different in greases than they are in lubricants?
Yeah, so in lubricants, you're often adding them either as a specific purpose, like the PPV, or you're adding them to increase viscosity and VI. And so they just need to go into the oil. In the grease, what they're actually doing is they're forming a network with the grease thickener to support each other. It's kind of like the polymer is the rebar in concrete. It's not, if you put in just the polymer, it wasn't going to make anything like a grease. If you put in just the grease thickener, it wasn't going to be nearly as effective as if it was supported by that polymer. And so you're really looking for things that can work together and support that. And when you do it right, things that polymers can add to a grease, they'll reduce oil bleed. They can increase the stiffness of the grease for much more efficiently than just adding more thickener. So you can save costs that way. And then polymers, depending on the thickener and the application, can be very good at preventing like a water spray off, water washout sort of effect in grease.
All right, I like that analogy of the rebar because I think that's one that everyone can kind of understand conceptually. when we're talking about those kinds of polymers that are working with the thickeners, is there a particular family of chemistries that is typical of that application?
Uh, it really depends on the thickener, and it also depends pretty strongly on the base oil. A lot of people talking about greases will talk about thickener type only and kind of ignore the base oil. It does matter. You're going to get a lot different properties using a naphthenic base oil versus a paraffinic versus a PAO. Um, and it's hard to make specific recommendations outside of specific cases. I will say much more than in liquid lubricants. I see the styrene copolymers used in greases much more often than I see them in the, the liquid lubricants. Styrene in the wrong concentrations is pretty quick to make gels, which is not what you want in a liquid lubricant, but kind of a gel network supporting that thickener network can be very effective. And then those like pi stacking of the rings on styrene can interact with certain thickeners and really help compatibilize the oil in there, prevent oil bleed, a lot of that. So I do. It's not a universal solution. You don't always want styrene, but more often than I see it in liquid lubricants, I see styrene in greases.
Yeah, interesting. Okay, and I'm glad you brought up the issue of people overlooking the base oil when they talk about greases, because even the language that we use to describe greases is always about the thickener and the NLGI grade, and often even on
Yeah,
like the TDS they won't even mention what kind of base oil is being used. But like you said, there is a lot of variability. I mean, there's plenty of naphthenic based greases, versus paraffinic based greases or synthetic style PAO ones as well. And yeah, we place such a huge emphasis on that in the lubricants world, but for some reason, when it comes to greases, we kind of just ignore it, even though the base oil is responsible for much of, I won't say all, but much of the lubrication that takes place. Um, okay, now I always, as we sort of end up these conversations, like to take a look into the future of a particular topic. In your case, with polymers, it's obviously in some ways, a very narrow, but in some ways also extremely broad topic, because you have so many chemistries that are available to you. When you're talking about the world of polymers, it's basically infinite. Um, is there anything that you're seeing on the horizon, or that Functional Products is working on? Um, are there any kind of developments in lubricants polymers, um, or even the types of chemistries that are becoming available on the market? What should we be looking forward to?
a lot of the recent work I've been doing, we've been looking at a lot of polymers as heavy base stock replacements for very high end applications. Things that almost look like base stocks, like your MPAOs or your bright stocks, that are in fact polymers. Uh, just new ways to use those polymers and then solve problems, especially in uh, shear sensitive applications, or moving forward into EV, all the instant torque and things give a lot more shear. So the smaller, more base stock like polymers have been becoming more and more popular, and learning how to use them for different things has been kind of a big push. Recently, we've been working a lot with EPOs, that are called ethylene propylene oligomers. They are honestly bigger than some of the other polymers we use, but the industry calls them oligomers. So here we are. Um, but they shear more like a heavy base stock, but they provide very efficient thickening, and they're very stable at high temperature, uh, which again for this upcoming electric vehicle applications and things is becoming more important. Uh, but it's not just your temperature range has shifted up. It's also they're pretty good at low temperature as well. So they've got that kind of expanded range in general. Um, Makes them very nice to use. So it's kind of a combination of thickening efficiency and that widened range and the low shear. They're getting into a lot of formulations. And let's see, try to think of
Yeah.
some examples of things we've done recently. They're pretty versatile. So we've used them in hydraulic fluids like ISO 32, ISO 46 hydraulic fluids, in some gear oil up to like SAE 140 grades, which is getting a little heavier. And then way at the other end of the spectrum, we've been able to use that chemistry in sugar mill oil, which needs to be ISO 20,000 or higher. Just so it's kind of run that gamut of, it's got a wide range of use cases where it does provide a real benefit for the cost.
Yeah. I think maybe what's helpful as well for some listeners to this podcast who might have an end user background. So one of the big changes that's going on in the industry at the moment, and one of the reasons that Jacob was talking specifically about, let's say, heavier base stock replacements, is that okay, some background here. In order to get a reasonably high viscosity, let's say industrial gear oil, something like a 320 or 460, most of the time we're looking at for a mineral base oil, we're looking at having to use something like a Group 1 bright stock. And bright stock availability has been declining all over the world. And there isn't really kind of like a Group 2, Group 3 replacement for that kind of heavier grade. So if you are looking at kind of, I guess, formulating a mineral oil that is not Group 1 based, but you still want an ISO 460, then you're looking at sort of, a Group 2 or a Group 3 boosted with some kind of polymer a lot of the time to raise the viscosity up. So that's kind of one of the challenges that the industry is facing. And there are actually some base stock developments on the way where there is kind of like the equivalent of a Group stock, a Group 2 kind of heavy neutral, which will enable some of those heavier industrial formulations. Okay, well, hey, Jacob, I think that's been really enlightening. It's been nice to sort of get into the technical weeds about a range of the different polymers that are available to us. Because like I said, on the end user side, for the most part, polymers are completely invisible to us. We really only see their bulk effects in the formulation, but from a used oil analysis standpoint, they're kind of invisible to us. So getting a bit of a window into all of the different properties that they impart to both lubricants and greases has been extremely helpful. So Jacob, thanks so much for coming on, and we'll have to get you on for some more specialized polymer work in future.
Thank you.